Can I start?
Yeah.
Perfect. All right. Thank you everyone for being here. My name is Karnchanachari. I'm senior engineer at Motional, where I lead the nuPlan team. One of the many things that we do as the nuPlan team is running and hosting the nuPlan Motion Planning Challenge that I'll be going through today. So a quick run through. Well, first I'll give you an introduction of Motional, what we do, how we went and collected the data set and curated it for us to release to the public, how we built and designed the dev kit to accompany the data set, followed by how this all builds up to the challenge that we hosted, and we'll end with the finalist presentations at the end. So at Motional, we're building a level 4 autonomous driverless system. We developed this with collaboration with Hyundai on the all-electric Ioniq 5 robotaxi platform. The platform is equipped with over 30 sensors to enable fully safe autonomous driving operations. Over the past decade, we've hit a number of milestones. We've launched the world's first pilot robotaxi system service in 2016 in Singapore. We launched a public robotaxi service also on the Lyft network in Las Vegas in 2018. It is now the world's longest standing public robotaxi fleet. We became one of the world's first companies to go fully autonomous on public roads in 2020. And we also launched AVs for deliveries on the Uber Eats network. So over the past 5 years, when we've launched the service in Vegas, we've given over 130,000 rides where we achieved the vast majority of rides have been rated 5 out of 5 stars. So the mission here at Motional is to make safe, reliable, and accessible robotaxis a reality. So now onto nuPlan, the dataset, the dev kit, and finally the challenge. So nuPlan is an evolution of nuScenes. You've seen in previous presentations before where nuScenes has been referenced. We've released 2 iterations of it. First, nuScenes in 2019, our second iteration in 2020, and last year in 2022, we released the nuPlan dataset. The dataset contains 1,282 hours of human driving data. It's collected from over 4 cities: Las Vegas, Pittsburgh, Boston, and Singapore. A portion of this dataset is also released with sensor data. Lastly, we tag interesting events and scenario in the dataset. Some of these scenarios includes unprotected cross turns, dense vehicle interactions, jaywalking, lane change, pickup drop-off area, and vehicle following, just to name a few. The reason that we tag this is to enable quick and efficient evaluation of planners. So we want to be able to identify what scenarios and events our planners are good at, and more importantly, where we can improve. So how do we collect the data? As I mentioned before, we collected through human driving data. We sent the cars out to 4 cities and collected them all raw sensor data. We then processed it on our offline perception system. This is to remove real-time and memory constraints that would otherwise be present on the AV platform online. We use many LiDAR sweeps, and we look into the past and to the future to achieve a consistent tracking solution for detection of agents and obstacles in the scene. On top of this, we have traffic light information that is inferred from the agent's motion in the scene. And lastly, we have route information as well. The route information is inferred from the driven route by the human driver. And this is depicted as a sequence of roadblocks along the route. Next, we have the dev kit. The dev kit is a way for us to quickly access the data set that we provide. We developed a modular and scalable framework for evaluation and training. So I'll be mostly focused on the evaluation part here, but there's also the whole training side that you can read more on our website and directly at GitHub. So the evaluation framework, it's split into 3 main parts: the simulation, the metrics, and the dashboard. So the simulation itself has 4 components: the observations, The observation first is how we represent the world or the data detections to the planner, raw sensors or 3D boxes. Next, we got the planner. Under the context of the competition, this is what the contestants are providing us for the competition. This is also how we implemented our baselines for the competition as well. So it doesn't matter, it can be ML, it could be rule-based, it could be some hybrid platform that you design, it could be any planner. Next, we've got the agents. So how do we propagate the agents along the scenarios? The most simple way to do it is to do log replay. So simply taking the actions of the agents in the scene and just replaying it is the most common way of doing it. You can also propagate it through according some predefined path. We call this on rails, and that will just allow you to be more particular with how the agents are moving, although it then deviates away from the log. Lastly, we've seen in many presentations beforehand that you can do ML policies as well. There's many companies trying to do it to achieve realistic and diverse traffic simulations. Lastly, we've got the controller. The controller here can be the perfect tracking controller, which is simply taking the plan trajectory from the planner and interpolating along the plan path. This is somewhat unrealistic because if the planner decides to do something that's kinematically infeasible, then the car will simply teleport to that point. So we also provide a kinematic bicycle model along with a LQR tracking controller to simulate low-level control and the dynamics of car that would be present on real AV on real road. This also confines the movement of the AV to be kinematically feasible, leading to more realistic simulations. Like I said, it's modular, so we can configure this to be open loop and closed loop by selecting the modules that I've listed out here. Once we've run the simulation, then we pass it on to the metrics engine. The metrics engine here will calculate the metrics based on whether the scenario is ran in open loop or in closed loop. I'll go into a little bit more detail of what those metrics are in a later slide. And lastly, we've got the dashboard. And this is just how we visualize the metrics, time series data, and also the scenario itself. And you'll see some of the visualizations later as well. So to the challenge itself, it's a planning challenge, as the title suggests, but however, you can think of it as a prediction planning challenge as well, because the input to the planner are agent boxes, the map, the goal, and the route. So we don't provide the planners with any prediction. So any good planner will need to account for possible trajectories that the agents might take in simulation to plan accordingly. These are very important, especially like cross turns, Pluto areas where interaction with other agents is crucial. The planner module is responsible with outputting an ego trajectory, which is then fed back to the simulation suite, trying to track the given trajectory, pass through the kinematic bicycle model, and then this loop keeps going until the end of the scenario. Like I said before, the simulation or the evaluation framework is modular. So we've split this down into three main challenges. In challenge one, it's the open loop challenge, where both the ego and the agent simulation is in open loop. It's very self-explanatory. Everything's according to the log, even though the agent will plan, the ego will plan differently from the expert trajectory, will not deviate. And this is more similar to a motion forecasting challenge. In challenge two, we make the ego propagation closed loop. And similar to challenge one, in challenge two, the agent simulation is still in open loop, so it follows the log. And in challenge three, we have reactive agents. So now both the ego and the agent simulation are in closed loop. For agents policy, we follow the IDM policy, stands for Intelligent Driver Model. It's not an ML policy, it's a simple policy that describes how an agent should drive according to a lead agent, maintaining some sort of distance and targeting a velocity. So let's see how this looks in action. On the left, we've got open loop. The thing I want to point out is, as I mentioned before, the plan trajectory might deviate from what the expert route is in orange, but the ego will simply follow what was in the log. Here we compared the plan trajectory with the expert trajectory. In the closed loop non-reactive agents challenge, now the ego is in closed loop. What we have here is a situation where the planner drives considerably slower than it was in the log, leading to a false collision, as you can see here, where a lagging agent essentially collides and goes through the ego, leading to an unrealistic scenario. So to remedy this, we have reactive agents where now all the agents are aware of each other, and more importantly, the ego. So again, with the same planner that's driving a bit slower, the reactive agents are now respecting this change in behavior and accelerates a bit slower, not than avoiding the collision that you saw in the second graphic. So now we have all this. So how do we quantify the performance of AV? So we've got metrics here. The scenarios are given a score from 0 to 1, where a higher score indicates a better performance. For the better performance here is different for open loop and closed loop. Again, with open loop, we're taking inspiration from motion forecasting challenges. So we're taking metrics such as average displacement error, final displacement error over the position and the heading. As for closed loop, we have to be more sophisticated with the metrics, because in closed loop, the scenarios generally diverge from the log, and therefore you cannot really hold down only to the expert trajectory as the ground truth or the correct thing to do. It's not very easy to quantify what the correct thing to do is, but it's quite easy to identify things that it shouldn't do. So things that it shouldn't do, it shouldn't collide, shouldn't go out of drivable area, shouldn't go in the wrong direction, follows the speed limit. And the likeness to the expert here is we simply take a look at if the ego is making progress along the same route as the expert. And that's how we see if the behavior is somewhat similar to expert, but we don't really constrain the metrics to the expert directly. And lastly, we've got comfort metrics as well, just to guard for jerky planners. Now that we have the score for each scenario, we then aggregate them by just taking the average over the whole challenge. And then to get the final score of the entire challenge, we take the average of challenge 1, 2, and 3. So before we go to the results of the challenge and see what the finalists did, I want to show you the baseline that we set up for the challenge. We have 3 baselines in total, 2 rule-based, 1 ML-based challenge, baseline, sorry. First up, simple planner. As the name suggests, it's very simple. Plans in a straight line, constant speed. The only logic that it has is it will decelerate if the speed is faster than the max velocity that's set for the planner. Quickly here, you'll notice that the scenario here is tagged as starting right turn. And the planner is supposed to turn right into the pickup drop-off area. But because it's simple planner, it completely ignores that and goes straight through the intersection, thus failing this scenario. So adding a bit more sophistication to our rule-based planner, we've got the IDM planner. Again, IDM stands for Intelligent Driver Model. So we're using modified policy for the reactive agents for this and repurpose it for this planner as well. So there's 2 parts. First part is the breadth-first search path planning, which simply plans a path along the route towards the mission goal. The second part is the longitudinal velocity control. Here, the planner takes a look at if there's a leading agent. If there is, then it tries to maintain some distance, a safe distance. If not, then it tracks a velocity. Usually we pick the speed limit for this. As you can see, the starting right turn, this planner has no problem and simply takes a right towards the pickup and drop-off area. However, it's not all powerful. There are still scenarios where it does fail. And here is an unprotected turn, a relatively complex situation, and has reason to wait for oncoming traffic before turning. As you can see here, that it simply collides onto the oncoming vehicle at the front there. So next up, we've got our ML-based planner, which is based on L5 Kit's implementation of Urban Driver. We implemented our own version in nuPlan, and we trained it in open loop. It takes a vectorized input of agents and map. It passes through a global attention mechanism that predicts the ego trajectory. During training, to account for the distribution shift In closed loop simulation, we apply some data augmentation to the agents and to an expert trajectory so that can drive in closed loop. What you'll see here is like actually the reverse of the IDM agent. First, we saw that the IDM agent can turn right just simply fine, but now we find ourselves with the ML model struggling to making a simple right turn. However, in the unprotected turn, it actually reasons correctly to wait for oncoming agent before turning onto the intersection, crossing it onto the pickup and drop off area. So here are the challenge results. These are the distribution of the overall scores of all the submissions. We had 52 in total, or from 11 countries, from 21 institutions in total. Here are the scores of our baselines, where Simple Planner, unsurprisingly, came in very low, IDM at middle of the pack, followed on by Urban Driver at 0.75. So let's break it down challenge by challenge. First, we've got the open loop challenge. What you'll see here is IDM and Simple Planner performing very poorly, and then Urban Driver actually doing really well. The reason for this is the open loop challenge favors imitation learning based method, especially if your planner is trained on the nuPlan data. It learns the action that the driver usually takes for each snapshot and tries to imitate it, thus scoring fairly well in the open loop challenge. So rule-based planner here ignores this entirely and plans according to its algorithm, and therefore performs really poorly on this challenge. For the closed loop non-reactive challenge, we see that now the IDM planner is now performing much better. The Urban Driver performing less good, but comparable to IDM planner. But what we see is both learning and rule-based planner perform well, but the best strategy so far, based on what we've seen from our own experimentations and what we saw from the submissions, which did better than both the IDM and Urban Driver, are hybrid methods. Methods which combines both ML and some processing, whether it's pre-processing or post-processing of the trajectory to smooth it out through an optimization, some collision checking to perform well in both open loop and closed loop. Lastly, we've got the closed loop reactive challenge. Here, the score tends to improve. And the reason for this is the reactive agents tends to yield for the ego vehicle, avoiding collisions, and thus improving the score. Lastly, before we move on to the presentation of our finalists, let's just compare the top three side by side. This is not listed in no particular order. If you haven't seen the leaderboard, then you won't know who the winner is, but if you've seen them, then it's pretty clear. But what I really want to point out here is it's a fundamental behavior of just coming to a stop in a dense traffic scenario. The middle one from CS2TU actually nudges to the left. It's left to avoid the lane changing vehicle. The auto horizon planner comes to a stop perfectly fine. But then we have Pegasus, which drives a bit slower, and we saw the exact same scenario as we saw before, which leads to an unrealistic scenario. Next, we have the unprotected turn that we saw before. As you know, it's a challenge scenario, but all three planners here manages to traverse this scenario just fine, all with different flavors. The main difference here is that I see is CSTU actually inches much closer to the oncoming traffic compared to the other two. The Auto Horizon Pegasus planner actually managed to go through just fine, reaching the pickup drop-off area, while the CSTU one lags behind a little bit, but at least avoids all collisions. So that brings me to the end of the nuPlan intro overview part. So let's move on to the finalist presentations. So the Innovation Award first, and this one goes to Team AID with the Gameformer Planner. Unfortunately, the team couldn't be here today, so I have a video from them describing their approach. There's no sound.
output should be the handbook.
Professor Cherry. If you would like to learn more about our research, please.
All right, let's start again.
Hello, my name is Zhi Huang, and I am delighted to present our solution for the nuPlan challenge. First of all, allow me to introduce our team, EID, which stands for Automatic Intelligent Decision Making. Our team consists of myself, Hao Chen, Xiao Yu, and our advisor, Professor Chen Li. If you would like to learn more about our research, please visit our lab's homepage. And if you are interested in our solution, it will be open source in GitHub. So now let's delve into our proposed planning framework. The framework is built upon GAN-form model, which we designed for interactive patient planning. It has also demonstrated stellar performance on the remote interaction patient benchmark. The planning framework has the four key steps: feature processing, task planning, model query, and trajectory refinement. Firstly, we retrieve information from the observation buffer and map API from the nuPlan simulator. We process this data to obtain patient history and a vectorized set map of it. We then get necessary information such as roadblocks, obstacles, and turbulent states to perform path planning, ultimately generating a reference path for eagle view. Next, we feed the processed features into the GAN-form model. This model generates multimodal junction trajectories for the surrounding agents and an initial trajectory for the eagle view. We project initial eagle trajectory onto the reference path, as well as most likely prediction results of other agents onto reference paths in free net space. This process yields a spatial temporal path occupants for a subsequent trajectory refinement process. Finally, we utilize a nonlinear optimizer as the planner to refine the eagle's motion plan. This step can help avoid distributional shift or causal confusion, which are often encountered by measurement-based planners. The optimization space considers a wide range of factors, including speed limit, acceleration, jerk, final displacement error relative to the initial plan, and most importantly, collision avoidance. The final optimized trajectory is then transformed back to the consistent space and executed within the simulator. At the core of our planning framework lies the GAN-form model, which utilizes the concept of level K gap theory to model the mutual influence among agents' behavior in the future for joint prediction and planning. It is a transformer-based encoder-decoder network. The encoder part uses transformers to extract the relationships between agents and map elements. The core idea of GAN-former is that we use a series of transformer decoder layers to iteratively decode the trajectories of all agents and iteratively refine the interaction prediction process using the previously obtained information from the last level. Specifically, at level 0, all agents act rather independently without the future information of the agents. And then at each decoder level K, the decoder receives the predicted information from the previous layer, as well as the current background information from the encoder part. For additional details, please refer to our preprint archive. For the results, our planner has achieved competitive performance on the nuPlan challenge leaderboard in terms of the overall score. It also shows top performance on some key metrics in both open loop and closed loop planning tests. We also visualize the closed loop testing results on several challenging urban driving scenarios, which demonstrate our planner's effectiveness in handling complex and interactive driving situations. So that's all about our solution. Thank you very much.
So the Innovation Prize winner, Team EAD, came in at a score of 0.829, which coincidentally also was the 4th place of the competition. Next, we have 3rd place, honorable runner-up, Team Pegasus with a multi-path planner. Unfortunately, they are also not here today, so I have a video from them describing their approach.
Hello everyone, I'm CVPR23. I'm coming from Pegasus. Pegasus is an autonomous driving company. We have an office in Shanghai and San Jose. Our method is based on reinforcement learning, utilizing data augmentation and post-processing to achieve better performance. First, let me introduce our model, which is largely based on the scale of art waveform movements with reductions. For the input feature, we use vectorized map representation. For the diffusion encoder and neutrality, we build different types of input feature. Latent query attention is used to reduce computational cost. To represent multimodal output, also mixer model with predefined visual query is used. For more detail, I recommend referring to the original reform tool. To improve closed-loop performance, data augmentation is important. Generally, the newly generated trajectory include past and current states that demonstrate how the rate reach the derealization, and future states that indicate how to drive back to the export trajectory. For past and current ego states, we found that past ego states are not important in our program. The model, with or without past ego states, can achieve similar results as demonstrated in the right table. Therefore, in our model, the ego input only includes the current state, and random noise is introduced for data augmentation. For generating future trajectory, we apply two methods. One is generating a smooth trajectory, which converges to the ground truth. This can be done by truth optimization. The other is directly using the ground truth. Both methods achieve similar results. Therefore, for simplicity, directly using the expert trajectory is a good choice. Despite using the train model with data augmentation, the planner still not work well in closed-loop scenario. As shown in this video, the ego vehicle exhibits large understeering. With closer examination, we can see that the plan trajectory is reasonable in every field, as shown in the figures, even if it deviates from the expert trajectory. However, the ego vehicle does not follow the plan trajectory exactly, and the deviation accumulates gradually. Moreover, this needs to occur with both two-stage controller and perfect tracking controller, indicating that it is not caused by the controller error, but rather comes from the neural network itself. Here, we propose a workaround that can somewhat alleviate this problem, and we hope other teams may have better solutions. This trajectory in every frame is generally okay, and the error accumulates gradually. Using a lower planning rate may slow down error accumulation. In the default setting, the planning rate is 0.1 seconds. We reduce the planning rate to 2 seconds. The video in the right demonstrates the effect. However, handling with lower planning rate reacts more slowly to environmental change and potentially leads to more collision. Therefore, we add a post-collision check. If a future collision is detected, we immediately replan. Finally, as shown in the table, with post-processing and the data augmentation, our planner performed well in closed-loop program for validation dataset. Thank you for your attention. If you have any questions, please feel free to email me.
So that was Team Pegasus, came in at 0.848 at third place. Next, we have second place honorable runner-up, Team Auto Horizon with the nuPlan planner. We've got Ihan here to present his approach.
Good afternoon, everyone. I'm Ihan Hu, and today I will be sharing our second place solution, imitation with spatial temporal heat map. It is a joint work with my teammates, Kun Li, Pingyuan Liang, and we are from Horizon Robotics. For overall structure, our approach consists of a neural network predictor and a set of post-processing algorithms. In form of multitask learning, the neural network predictor takes raster image and input and output the heat map, occupancy, and the initial plan trajectory. All this information is then fed into the post-processing module for optimization to generate a safe and smooth plan. Specifically, we use ResX50 as our encoder and use UNet as NAC. As shown in the image on right, we adopt an input raster with 6 channels, which capture the ego states, surrounding dynamic agents, static environments, navigation, and roadmap information. This type of encoding is simple, intuitive, and comprehensive. As shown in the image below, we represent a planned trajectory using spatial temporal heat map, where each pixel represents the probability density of ego vehicle, and each channel represents the probability of different time steps. This representation is effectively captured the uncertainty and multimodality in complex driving scenarios. Similarly, to effectively model the motion of surrounding dynamic objects, we predict the occupancy probability of dynamic objects at each time step. As shown in the video on the right, the occupancy prediction plays a key role in collision avoidance in complex and dynamic driving scenarios. For training, we adopt a multitask learning strategy and takes a weighted sum of these losses. Simultaneously, we inspired by ShuffleNet, we employed perturbation as data augmentation under the dynamic constraints. To better serve the downstream pole servers, we fused the future ego poles, future dynamic agents, static objects into a collision avoidance map, as shown in the right. Specifically, we constructed an ego kernel based on the ego car poles, and then perform convolution on the long drivable areas to obtain the collision avoidance map. The entire operation can be implemented with convolutions, and it's run extremely fast with GPU. Then we utilize a pole server to consolidate the above information and refine the final plan trajectory. Inspired by E2EAD, we use Casati IP-opt solver to find the optimal trajectory considering the initial trajectory, collision avoidance map, heat map prediction, comfort, and ego vehicle's dynamic constraints. This type of pole server steers the trajectory away from unsafe areas and ensure the final safety and comfort. Here is our application study. We can see that the perturbation, heat map representation, and pole server all contribute significantly to the improvement of the results. Particularly, the pole server with occupancy is the most effective for the closed loop results. Our methods rank second on the leaderboard and achieves the best comfort and ego progress score. The methods demonstrate that our method is good at balancing the ego progress, comfort, and safety. Since the first place is rule-based, so we could say that we are the highest learned methods in the leaderboard. Thanks for your attention. Since time is limited, if you guys are interested, please refer to our technical report for more details. Thank you.
Thanks, Jan. So the team Outer Horizon came in at 0.875, only 0.02 shy from the first place. So for our first place outstanding champion is team CSTU with the PDM planner. So we've got Marcel here to present his approach. Go on. Yeah, hi everyone. I'm Marcel Hallgarten. I'm going to present the predictive driver model on behalf of my team. And this was joint work with Daniel Dauner, Kashyap Chitta, and Andreas Geiger. So the starting point for our method was this simple benchmark that we conducted right at the beginning with some baselines that we had available, where we found that these ego forecasting learned planners perform quite well in open loop, but in contrast, they are outperformed by the very simple and quite old intelligent driver model in the closed loop evaluation. Also, we found that not even the log replay planner that has access to the ground truth future trajectory was able to achieve perfect score in the closed loop evaluation, indicating that the controller is unable to accurately track the trajectory that's output by the model. So that's why we decided to pursue a hybrid approach, relying on two separate planners. The first is our PDM closed planner that is responsible for planning the short-term trajectory based on a rule-based planning approach. And the second is a ego forecasting learned planning approach, which we call PDM open. And we came up with two strategies to combine the outputs of both planners. So the first is what we call an adaptive interpolation, where we basically infer both planners and then take the output from the PDM closed planner up to a certain horizon, and then append the output of the PDM open planner. And this cutting horizon can be either fixed or adaptive to basically how the deviation between the current state and the past predicted trajectory is, so it can account for the drift of the controller. The second way is to not predict a trajectory with the PDM open model, but instead feed the PDM closed trajectory also to the PDM open feed the PDM closed trajectory to our PDM open model and regress offsets rather than exact waypoints. So this is what our rule-based PDM closed model looks like. In the first step, we identify a sequence of central lines leading to the navigation goal by a graph search. Then we forecast surrounding agents with a simple constant velocity forecast and generate different IDM proposals. In total, we evaluate 15 IDM proposals obtained by 5 longitudinal IDM proposals, each combined with 3 lateral offsets from the center line. We then simulate these proposals to obtain the expected outcome of the controller and score them with a cost function that closely resembles the nuPlan metrics. And finally, we select the highest scoring trajectory as the output of the model. For the learned long-term ego forecasting part, we use this very simple and lightweight MLP-based model, which takes just the center line points as an input and the ego history. And we observed that these inputs are enough to accurately forecast the ego trajectory. So adding information on surrounding agent even made performance worse. And we use a very simple model for this ego forecasting. So it's a simple 2-layer MLP model with 512 hidden neurons in each of these layers. So it's very simple and lightweight. Still, we found that this lightweight PDM open model was able to outperform the baselines in the open loop evaluation, while the PDM closed model also significantly improved upon the IDM model in the closed loop evaluation. Also, the PDM open model considerably improved in runtime compared to the other models. Our PDM hybrid model then is able to effectively combine the strengths of both models, leading to state-of-the-art performance on the nuPlan benchmark. If you found this interesting, then make sure to check our code and also our paper. And if you have any questions, then feel free to approach me later. Thank you. Thank you, Marcel. Congrats on first place. They came in at 0.895, topping our leaderboard. Here's a quick overview of our finalists and the Innovation Award today. So some closing remarks. For future works, we'd like to improve on controllers. As we saw there, our tracker is definitely not perfect. So we'd like to see an MPC controller, something like this that can improve our tracking performance. We like to diversify our metrics. So our metrics are definitely not comprehensive at the moment, and improving it to really distinguish and discriminate between good from great planners. As you can see also from the finalists today that the scores are already saturating the top end of our scale. So being able to stretch that out and really depict good from bad planners would be very valuable. Next is to improve on our reactivations by employing some ML policy to increase realism and also simulate more diverse and simulate the long tail problem as well. We've been asked about RL training a lot. Yes, we can look to implement some gym-like simulation, and more importantly, apply some offline learning, offline RL using our data set. Lastly, now that since we have the sensor data released, we can also look to do some end-to-end planning challenges as well in the future. If you're interested to keep track with us, keep up to date, please visit nuPlan.org to download our data set and check out our dev kit at github.com/motional/nuPlan dev kit. Quick thanks to Shanghai Artificial Intelligence Lab and Mars Lab for organizing this workshop. Quick special mentions to Dimitris and Holger for helping set up and run the challenge, Hongyang Li and Hang Zhao for inviting us to be part of this workshop. The workshop organizers themselves, of course, for setting all this up, the challenge participants for making the nuPlan challenge happen, and finally, the team at Motional, nuPlan team. This would not be possible without you. This project has been 2 years in the making, all the way from data collection in 2021 up until building up the dev kit and now concluding the competition here today at CVPR. Lastly, we're hiring. We've got sites in US, Singapore, South Korea. We've got on-site, hybrid, and remote positions. So if you're interested in what we're doing here at Motional, whether it's nuPlan related or otherwise, please visit us at motional.com/careers. Thank you so much for listening. Have a wonderful rest of your afternoon.
Great challenge organization, and next we'll have Yuning to give a presentation. Yuning.